Welcome everyone. You are joining us for laser measurement solutions for materials microprocessing applications. This webinar is sponsored by Ophir, LaserPoint SRL, and DataRay Inc., and it is hosted by us at Photonics Media. Today you're going to hear from Mark Slutzki. He is a product manager for power and energy measurement solutions at Ophir and has been with Ophir since 2004. Prior to this, he held similar positions in the semiconductor and telecom industries. He served in the Israeli Air Force as a research physicist, working on special projects, and has a degree in electro-optics and applied physics. In this session, Mark is going to talk about innovative solutions for the challenges that accompany materials microprocessing applications. You can ask questions or leave comments in the chat box at any time. If you have any technical issues during the event, please log out and back in to rejoin. You will be able to access the recording of this webinar online after the event, and you will get links to that recording in your email inbox. So with nothing further from me, I would like to welcome Mark Slutzki.
Okay, thanks, Joanna. Thanks for the introduction. And hello, everyone, and welcome. There we are. All right, I have to say that I'm well aware of how busy everyone is, and I genuinely appreciate the fact that you've taken time out of a very full day to join me in this conversation. Thank you for the interest and the vote of confidence, and I trust and hope that, God willing, it'll be a worthwhile investment. So just add, I timed myself this morning. The presentation should take around 35, 40 minutes, something like that. Many, I'd even say most of the people that we at Ophir work with are not necessarily laser physicists doing research on lasers, but rather professionals working in some application area in which the laser is used as a component, maybe a critical component in making some laser-based process happen. I'm guessing that that probably describes many or most of you. Material microprocessing is a relatively new subset of material processing that enables you to do some pretty unique things. But when you want to control the process by monitoring the laser, there are some unique challenges that can unexpectedly leave you with a fried laser power sensor. So it's for people like you then that I'm hoping to share some insights that can hopefully help you better understand what makes these laser processes different and how to take that into account so that you can measure and monitor your process and keep it running smoothly and profitably. I should just mention, just outside my door are two-year-old grandsons, and a newly born granddaughter is due in the house any minute. So if there should be a unexpected breach in security and the door is popped open, my apologies in advance while I will get up and go reclose it, but hopefully that won't happen. No complaints about that sort of thing. Okay, I'm assuming you're at least somewhat familiar with Ophir. Some years back, we were acquired by Newport, and then Newport, together with us, became part of MKS Instruments. I should mention that I've tried to keep the information as generic as possible. I very much love the company that I work for, but our goal here is to share insights that'll be as helpful as possible to as many of you as possible. Having said that, I'm sure you can appreciate that when I do use examples of actual real-life solutions to illustrate some point, those are going to be obviously Ophir solutions because those are the ones that I'm able to talk about. So here's what we're going to be looking at. First, I just want to briefly talk a little bit about the need and what's motivating this new type of application. A few words, high altitude overview of the why and how of process monitoring. And then we'll get into the meat and potatoes. We'll talk about the challenges that are involved in measuring ultra-short pulse laser beams, which are central to making these kind of applications happen. We're going to explain all of this. And then we'll have a look at some of the new innovative solutions that are now becoming available. So let's begin with the beginning, and let's just talk a little bit first about the need. So before we discuss micro material processing, let's just first consider regular material processing, and then we'll see how the uniqueness of micro material processing comes into play. So we have a laser beam and some kind of a focusing optic. The beam gets focused down, and over here is where we place our target material. The beam might be CW, it might be pulsed, depending obviously on the specific nature of each given application. It's the heat, in essence, that makes the process happen, that burns, melts, vaporizes, zaps the material inside this space. In this space is where's my cursor? Here is the space within which the power density, and therefore the heat density, is high enough to do the work that we want to do to have the required effect on the target material. The quality of our result is going to depend on how well we're able to control the shape and location of this space. So it's the heat density that's doing the work. This is a kind of a brute force sort of a process. In micro material processing, we're looking at applications where we need a bit more of a delicate touch, either because we're dealing with more delicate materials or we're trying to create more delicate features, or both. Think of the difference between a carpenter building a house and a carpenter, crafting fine furniture, if you will. So some examples can include certain kinds of laser marking and engraving, cutting the cover glasses for smartphones. I think those qualify as delicate, drilling via holes in printed circuit boards, separating a flexible OLED display from the glass substrate on which it was manufactured, a process that's also known as liftoff. Okay, so we have an application requiring a delicate touch. Now, let's remember, inside that space within which the power density is high enough, I'm vaporizing or cutting or otherwise zapping the material. Outside that space, outside this space where the process is happening, I might not be vaporizing the material, but I'm certainly affecting it due to the heat. During the course of the pulse, certainly in a continuous beam, but even if it's a pulse beam, during the course of the pulse, the heat spreads. Here we see what's known as the heat affected zone. Okay, think of eye surgery as an illustrative and kind of scary example. I want to process the material at the target location, but outside that target location, I don't want to affect the material at all. Okay. In addition, there's another point that we want to keep in mind, and we're going to come back to this momentarily, and that's the fact that all the heat that leaves what I guess we'll call the process zone and moves into the not process, but nevertheless heat affected zone, that heat is not contributing to the process at all. That heat's going to waste. So there's an inefficiency issue that we want to, kind of keep on the radar screen as well. The solution that the industry has come up with is to use ultra-short pulse beams, by which I mean beams whose pulse widths are nanoseconds, picoseconds, and even femtoseconds. Now you'll notice that I put nanoseconds in parentheses. Up until not so long ago, nanoseconds were considered really short. Now they're already, certainly for the purposes of what we're discussing here, almost even borderline. Ultra-short pulses keep the heat-affected zone very small. As you can see, the difference between the heat-affected zone when using a long pulse laser and an ultra-short pulse laser. The short pulse duration means that the heat during the pulse has no time to dissipate to the surrounding material. The target material is locally exposed to a high enough instantaneous power density that it gets zapped before the heat has a chance to dilute, as opposed to with a longer pulse where the instantaneous power density will be lower and it'll take more time for the material to get zapped, and during that time the heat will move through the material, leading to a less well-defined area. And also, more energy per pulse is therefore going to be needed to get the same work done. In other words, a 1 microjoule pulse, for example, in a femtosecond pulse laser will do more work than the same 1 microjoule pulse in a microsecond pulse laser, and the result will be cleaner. Okay, let's remember that power is energy per time, right? A watt is a joule per second. So when we're talking about instantaneous power, as the pulse becomes shorter, the instantaneous power, not to be confused with average power, but the power during the course of the pulse becomes bigger for the same given energy. By keeping the absorption, by confining the absorption to a very tight space and time, the process happens inside a very tight space and time. So each pulse is now carrying out a process. And now, if we want to increase our throughput, all we need to do, I mean, everything sounds easy when you say it fast, but we can increase our throughput now by increasing the pulse repetition rate. So in these kind of applications, we're typically looking at lasers that are pulsing at pulse rates of a couple hundred kilohertz, maybe into the megahertz, and average powers are typically on the order of somewhere between a few tens of watts and a couple of hundred watts. So far, so good. However, in these physical conditions, some funny things start to happen. In normal conditions, normal things happen. A photon is either absorbed and imparts its energy to the material, or it's not absorbed, it passes through the material because the material is transparent to that wavelength. In general, a material is transparent to a given wavelength when the energy of a photon of that wavelength is smaller than the available energy levels in the atomic structure of the material, and the photon slips through. I am simplifying things. I might just mention that those last two sentences in their unsimplified form are what earned Albert Einstein his Nobel Prize in Physics. Figuring that out was a very big deal. In ultra-short pulses, say picoseconds and downwards, where the instantaneous electromagnetic field is very high, the likelihood of non-ordinary effects starts to increase. And now, non-ordinary effects can be, for example, the absorption of 2 or 3 photons together as a single absorption event. While the material might be transparent to a single photon at that given wavelength, and therefore at that particular energy, 2 or 3 photons together have more energy and can find maybe available energy levels to absorb the energy of those 2 or 3 photons when they're holding hands. This means two things. A, materials that would otherwise be transparent to this wavelength can suddenly become absorbing. And B, keep in mind, if you're not familiar with this, don't worry about it, but the energy of a photon is proportional to the frequency of the electromagnetic wave, or inversely proportional to the wavelength. So long wavelength photons like red light have less energy per photon than photons of blue light or ultraviolet light. Shorter wavelength, higher frequency, higher energy. Okay, don't sweat it, but it helps to keep that in mind. So 2 or 3 photon absorption has the same effect as reducing the wavelength by a factor of 2 or 3. In other words, we're increasing the effective photon energy by that factor of 2 or 3 or whatever it may be, giving the photons perhaps the ability, or at least more of an ability, to break up the atomic structure of the target material. This is similar, by the way, to how UV radiation is harmful to our skin. A sunburn is not because of more thermal energy that was absorbed in our skin. It might even be less total energy, but each of those photons packs more of an energy punch. So keep in mind, we're not talking about thermal effects, but a different mechanism. Now, this allows processing of materials that might otherwise not have been processable, if I can use that as a word, to that wavelength. And besides improving existing processes, it enables the development of some pretty nifty new processes. Here's an interesting application I came across a while ago, certain types of marking of syringes, medical industry. They use ultra short pulses which change the refractive index of the glass to give the visual appearance of printed material, printed symbols. Regular short pulses, even nanosecond pulses, would create micro cracks in the glass, but will not do the delicate work of changing the refractive index without affecting the surrounding glass. That was one hyphenated word. Those sculptures you sometimes see with the images patterned inside glass, right? Those are done using exactly such short but not ultra short pulses. The patterns that you see embedded in the glass are micro bubbles and micro cracks caused by localized heating. Exactly what we don't want in micro material processing applications. All this, as you can appreciate, creates some special requirements from the absorber that we're going to want to use in our laser measurement sensor. We'll come to that momentarily. First, I just want to show you a few examples of such process results. In this case, all produced by a few different models of spectrophysics, ultra-short, ultra-fast lasers, surface structuring of polymers, scribing on a silicon photocell, marking on peak polymer used in medical devices, just to give you an idea of what sort of things can be done using such ultra-short pulse laser beams. Okay, let's say a few words, as I said, high altitude, just a quick overview of the why and how of process monitoring. So back to our generic laser-based material processing application. My apologies for my artistic skills or lack thereof. So again, we've got a laser beam, we've got some focusing optics, and we've got that space inside of which the power density and therefore the heat density is high enough to do the work. And in the middle of that space is where we're going to want to put our target. Now, what happens though if the power changes, let's say due to aging of some component or due to shifting of some optical component in the beam delivery train, or focus shift, maybe because of heating effects changing the optical characteristics of the lens, we can suddenly find ourselves with our target outside the space within which the power density is high enough to do the work. Parameters that are not controlled can unexpectedly change what the process is doing and where it's doing it. And that can make your process unpredictable. And in the case of an industrial commercial process, it can eat into the profits that your process is supposed to be generating for you. So let's look at the parameters that help make these processes happen, the parameters that we want to keep our eyes on. In no particular order, the wavelength of the laser is going to define the amount of energy that's absorbed, transmitted, and reflected by different materials. Different materials absorb different wavelength light differently. Also, the minimal spot size to which we can focus the beam is proportional to the wavelength. That's something that comes out of physical optics. Since many materials exhibit high absorption in the UV lasers are particularly popular in these microprocessing applications because of their short wavelength. Average power translates directly into process throughput. If drilling one hole in a printed circuit board requires a certain amount of energy, then if our beam has such and such power, meaning this much energy per second, obviously that's going to set the upper limit on how many holes we can drill per second, using this setup. Laser power stability will determine the variability of the process around its desired values. This can manifest, for example, as differences in via hole diameter and depth and shape, and that's therefore going to limit the density of vias that we can achieve, again, with a given system, with a given setup. Laser pulse duration, we already talked a little bit about that, has a critical effect on microprocessing. As the laser pulse becomes shorter, the instantaneous power, remember the power during that pulse, becomes increasingly larger. So in our discussion today, we're focusing mainly on power and power stability measurements. So let's talk a little bit about the interesting challenges that are unique to ultra-short pulse beams. Okay, there are many ways to damage a sensor. I think there's some old American expression, there are many ways to skin a cat. I have no clue why one would want to skin a cat and how many ways there are, but I've heard such an expression. So the most obvious way to damage a sensor is overloading it, but that's kind of trivial. More relevant to our discussion is not so much too many watts or too many joules, but too many watts per unit area, watts per square centimeter, the power density, or too much energy density, too many joules per square centimeter. It's the power density and or the energy density, after all, that are processing our material. So if we take an extreme example, here you just see a nice example of thermal damage from a sensor that came in to us at Ophir for repair once. If we measure in or near the focal plane, and by the way, you'd be surprised at how often even seasoned professionals in laser-based applications can make that mistake. So if we measure in or near the focal plane, remember the focal plane is where we're doing our processing, we run the risk of material processing our sensor. And here you see a really neat, beautiful example of that. Now that's of course an extreme example. Anytime that the power density, again, the number of watts per square centimeter, let's say, is higher than what the sensor's absorber material can handle, we run the risk of causing damage. The damage may be slow and cumulative, and it may be quite sudden and dramatic. There are a few different damage mechanisms. The more well-known damage mechanism is thermal. Okay, too many watts per square centimeter, too many joules per square centimeter, you get the kind of burn marks that we just saw in the previous slide. Average power density is too high, pulse energy is too high, and so on. I should just say something important about too much pulse and too high pulse energy. Both of these, the maximum power density that a given absorber can handle and the maximum energy density, are both two different types of what we refer to as damage thresholds. It's very important to be aware that the maximum energy density damage threshold is not one fixed number. It actually depends on the pulse width. For a very short pulse, the heat that was generated by absorbing the beginning of the pulse has no time to get out of the way. By the time the end of the pulse arrives, all of that heat remains concentrated in a very thin layer of the absorber material, and the material can damage more easily if it's not rated for that kind of heat density, energy density. When there's a longer pulse, some of the heat that was created by absorbing the beginning of the pulse might, yes, have had enough time to propagate at least a little bit out of the way. And so we're not putting as much thermal stress on as thin a layer of the absorber material. So the maximum energy density depends, among other things, on the pulse width. It's the instantaneous power density, the power density during that pulse, that's actually doing the processing. That's what's bringing in the rate of heat coming in to that small area. In Ophir's data sheets, we normally specify the energy density damage threshold as not as the maximum instantaneous power density, but as a number of different maximum energy densities for a few different typical representative pulse widths. So here you see an extract of one of the sensor data sheets. So you can see for 10 millisecond pulses, which are common in certain industrial applications, this sensor can handle 2 joules per square centimeter. Whereas for pulse width less than 100 nanoseconds, it's only 300 millijoules per square centimeter, and so on and so on. We specify it this way simply because it's much easier for most users to know these two numbers, energy density, and pulse width, than it is for them to know the instantaneous power during the pulse, which is a number that most users probably don't really have in front of them. So just to make it easier and more practical for typical users, we specify it this way. Now notice how we stop at less than 100 nanoseconds. That's already the worst case damage threshold. The idea there is that once the pulse is so short that the heat generated by its absorption has no time to move out of the way during the pulse at all, From a thermal damage point of view, I'm going to say that again, from a thermal damage point of view, it makes no difference if the pulse is then even shorter. However, that's only from a thermal damage point of view. Our whole conversation today is about other mechanisms of damage. For ultra-short pulse lasers, there are non-thermal effects that can cause ablation. I like how we worded this short-term effect. It instantly zaps a certain thickness of layer off the material surface. Short pulse lasers in the picosecond and femtosecond range can have relatively low power and energy density, but can still cause significant damage to normal general purpose, let's call them sensors, due to the extremely high instantaneous power or power density. This is especially true, all the more so for UV lasers, where the photon energy is also high, and the photons can break molecular bonds more easily, as we said. So we've got a few different damage mechanisms here. Too high energy density, that's what we specify as the maximum energy density. That's one kind of damage threshold. Too high average power density, so many kilowatts per square centimeter. Average power, not to be confused with instantaneous power during the pulse. That's another kind of damage threshold, and those are listed in every sensor's data sheet, Ophir's and everyone else's. But then we also can have combinations of the above, all right? In many of the sort of applications we're talking about now, we can have pulse energies of some or many microjoules or tens or hundreds of microjoules, which is not something dramatic. Ultra short pulse widths and pulse repetition rates that can be a couple hundred kilohertz, a few megahertz. This combination brings down the overall, the bottom line damage threshold, because we've got multiple damage mechanisms all coming in at the same time. And this is a job for, that is when we need newer innovative solutions. So now let's look at newer innovative solutions. So first of all, as a basic background concept, sensor absorbers can generally be divided into two main types. We call them surface absorbers and volume absorbers. A surface absorber is an opaque material. In many Ophir sensors, we have surface absorbers consisting of some kind of a ceramic coating or various types of other coatings, or cemented on windows of specific materials, whatever. Now, let's say we have a Q-switch laser pulse width couple nanoseconds wide, and a pulse comes in with an energy density of, let's say 1 joule per square centimeter. By the time the end of that pulse arrives, the heat that was generated from absorbing the beginning of the pulse has not yet had time to move out of the way. And all of that heat is therefore concentrated in a very thin layer of this opaque surface material. We're talking about a layer probably only a few atoms thick. And the material had better be able to handle it and take it, or there's going to be damage, there's going to be burning of the surface material. On the other hand, for a longer pulse, let's say a couple hundred microseconds, milliseconds, by the time the end of the pulse arrives, the heat that was generated by absorbing the beginning of the pulse has, yes, had some time to propagate at least a little bit of the way into the thickness of the material. Doesn't need much. And so you don't have so much heat concentrated in so thin a layer of material. So short pulses can cause damage more easily than long pulses, all other things being equal. So the usual solution for short pulses with high energy densities is to use what we call a volume absorber. A volume absorber is a material that's not opaque, it's partially opaque. Good example, a very commonly used example, is your standard neutral density absorptive glass filter, NG, whatever it may be. The light gets absorbed incrementally as it moves through the thickness of that material. So no matter how short the pulse is, the heat is going to be spread out over a certain thickness of material because the absorption took place over a certain thickness of material. If you want a nice visual illustration of light being incrementally absorbed as it moves through a partially transmissive material, I love this photo. First of all, because it very nicely illustrates light being incrementally absorbed as it moves, in this case, downwards through the thickness of the material, in this case, seawater. But really, the reason I love this picture is because this is one of our sons and I around 12 meters down scuba diving in a scuba diving course off the coast of Eilat, the southern tip of Israel. I've not scuba dived anywhere else, but people who scuba dive all over the world tell me that Eilat really is one of the more beautiful scuba diving areas. I love it down there. But anyway, I digress. So with that concept in mind, there's constant work going on in Ophir, in other companies, and in other kind of institutions of developing, now that this kind of application is very quickly increasing in popularity, there's a lot of work going on to develop better and better absorber materials, each specially optimized for a pretty specific set of conditions. These materials are chosen, developed, whatever, for various specific material properties generally related to the size of the energy band gap in the atomic structure of the material. The specific optimum choice is obviously going to depend on a whole bunch of different parameters: the energy level, the pulse frequency, the repetition rate, the wavelength. As we all know, one of the first words you learn in any engineering curriculum is the word trade-off. There is no, not yet at least, there's no one material that is optimum for all conditions. So that's why there's lots of work going on all the time. So here are just a few examples from Ophir's lineup. Now, as I said in the introduction, the goal here isn't for you to memorize this chart and then go in order whatever it is. That's not the point. But it's to underline the complexity of the issue. We and others are coming out with more and more sophisticated solutions, but it is not trivial. Now, some of these are based on traditional volume absorbers. You'll notice increasing, the x-axis is the pulse repetition rate, the y-axis is pulse energy. So here, for example, is a pretty traditional volume absorber. The traditional volume absorbers, you'll notice, are more in the area of a couple of kilohertz or so, moderate energy levels, while others are for more, for increasing pulse repetition rates. And these are based on some of these newly developed innovative absorber materials. I should mention the new absorber that we call CM actually sits right on the sweet spot of many of today's micromaterial processing applications. A couple hundred kilohertz to a few megahertz, energies from microjoules, tens, hundreds of microjoules, just up into the near end of the millijoule range. That's pretty much a good description of very many of these material microprocessing applications, and that's really what this particular absorber was developed for. The one we call SV, you'll notice that it's also for high rep rates, but also for higher energies. This is really at the top of the line. SV is an acronym for surface volume, meaning it combines the best of both worlds. Again, the point isn't to remember the chart, obviously. The point is simply that with ultra short pulse lasers, you'll really want to consider a bit more in depth before settling on a given solution. And since this is a relatively new field, it would be a good idea to discuss the best choice for your particular set of conditions, your ultra short pulse application, with your measurement instrument manufacturer, so that you can be sure you're getting the right tool for the job, a tool that'll continue to operate accurately for many years, even under the very harsh demands of ultra short pulse lasers. And just before we conclude, just for completeness, it's worth pointing out that together with development all over the world of constantly better and better optimized absorber materials, there's also new approaches in instrumentation. There are some all-in-one instruments that are now making their way out into the market. Here you just see an example of an Ophir all-in-one instrument. Many of them include a removable diffuser to enable handling higher energy densities that make life a lot easier in some industrial scenarios like tight spaces, enclosed chambers where you can't, access to press buttons, or you can't use a cable or things like that. So just something to be aware of as well. Okay, so in summary, we talked a little bit about the need and the motivation behind, micro material. I'm not sure what the difference is. I don't know if I need to be so pedantic about it. Material microprocessing or whatever applications. It's evening time for me. We did a quick high altitude but still important review of the why and how, very high level review of process monitoring. And then we looked at some of the main challenges that are presented by these new types of lasers that make these new types of processes possible. And we looked at, the trend right now, some of the new solutions that are coming out, which are mainly focused on developing absorbers for laser power and energy sensors that are specifically optimized to be able to work in these kind of, under these laser conditions. I hope I've succeeded in my stated goal. Hopefully some of the basic concepts are now a little clearer for you. And even if you simply have a better idea now of what questions you want to ask your measurement instrument supplier, then I think that would already be a successful outcome from my perspective. So thank you very much. And with that, Joanna, I'll turn it back over to you.
Thank you very much. We do have time for a few questions before we close. Everyone, if you have not already, please go ahead and type your questions and comments into the webinar chat. All right, so my first question is, we use pulsed CO2 lasers for processing softer materials, organics, textiles, sometimes PCBs as well. Pulse widths are not short but not long. Pulse rates are high but not very high. Do we need to look into some sort of special sensor types you described, or can we use a regular type of sensor?
Okay. Right, the sort of pulsed CO2 lasers that are used in these applications typically have pulse widths on the order of some tens of microseconds, and operate at usually, rates of a couple of kilohertz. So that really is kind of on the borderline between what I guess we can call regular and not quite regular. Now, because of the long wavelength, the photon energy is less of a risk factor. Remember, short wavelength means high frequency, high energy. Long wavelength, ultraviolet can cause sunburns, red, not so much. So photon energy is maybe less of a risk factor, but the other factors that we talk about are, of course, still there. So anytime you're borderline, it probably pays to err on the side of caution, but it is, I mean, that's exactly where your question is coming from. Obviously, it is a kind of a borderline thing. I would err on the side of caution. Usually the kind of sensors that we're talking about aren't really, terribly significantly more expensive necessarily than the more traditional sensors, but they are optimized. So it would probably be worth at least taking a look at the specs. I should mention, by the way, that that new so-called CM absorber, which I had actually highlighted, that we recently developed at Ophir, it is calibrated out to CO2 laser wavelengths, out to 9.4 micrometers. Okay, there is a CO2 laser wavelength there, but it's not specified for wavelengths longer than that. After 10 micrometers, its absorption actually starts to drop. So it's another interesting point.
All right, thank you. This next question says, you mentioned various parameters such as wavelength, power, pulse rate, and so on. What about polarization? We use a fiber laser for drilling and had process issues that were eventually found to be the result of beam polarization. We added some polarizing filters and that solved the problem, but anytime we changed our power level, we had to sort it out all over again. It may be a bit off topic, but is this still in fact a real effect?
Interesting. Yeah, I guess it is more related to the application side than to the measurement side, but it's actually an interesting effect. It is known that polarization can affect the shape of drilled holes, and beams with radial or azimuthal polarization produce better shapes than beams with linear polarization. It's just a question of the physics of how the light is being absorbed in the material. For high power fiber lasers, typically, 1070 nanometers, something like that, one cannot generally control the polarization because the fibers are not really polarization maintaining. The beam is generally linearly polarized, but it's not stable, meaning the polarization is not stable, and it changes with fiber movement and bending. It would not surprise me to find out that the polarization can vary also with the power level. I don't think the manufacturers even check this, but it definitely sounds like something that is reasonable. In general, blue and green beams I know are linearly polarized and their polarization is also very stable. Same goes for CO2. For near IR wavelengths, 1064, 1070, it really depends on the type of laser, and it definitely makes sense to me that there would be an instability with power and maybe other parameters also.
Thank you. All right, this next question is, how do you convert continuous lasers into pulsed laser?
All right, that's a broad question. Again, doesn't really relate so much to the measurement side, but it's a good point to address. So you've got things like Q-switch lasers where that conversion is done inside the laser itself. You're building up more and more of what we call population inversion, and then you get this massive avalanche of photons coming out. Another way that's commonly done is that you have a laser that inherently is a continuous laser, and you're modulating the beam externally to where the beam's being generated. I suspect that that might be the case in many of these applications. In the ultra short pulse lasers, I'm not familiar enough with the physics of them, but there I'm pretty sure that it's happening inside the laser. You wouldn't be generating a femtosecond laser by putting an electromechanical shutter in front of a CW laser. So it depends on the laser. With these ultra short, I don't know, again, I'm not familiar with the physics of the innards of these lasers, but it's probably much more similar to how Q switching is done than to how chopping is done. But I don't really know. That's a very limited answer, but that would be the direction, I suppose.
Thank you. This next one asks, can cooling vents or chambers be used to reduce heat zone?
That's an interesting one. My first thought would be that I doubt it because we're talking about small heat zones that result from pulses that are lasting maybe some nanoseconds or microseconds, and during those few nanoseconds or microseconds, the heat's propagating through the material. So we're probably talking about a heat affected zone that's not a few millimeters in size, but probably more like micrometers. So I doubt that environmental temperature would really have much of an effect. I suppose if it's a cool chamber, although I'm not familiar with an application that would need that, maybe that would be different. But because of the kind of order of time magnitude that we're talking about, my gut hunch is that I doubt that controlling the temperature in the surrounding air, if that's what you mean, would really have any significant effect here.
All right, thank you. All right, and this last question is just asking if they said, notice the confidential notation at the bottom of the slides. Is this a confidential presentation?
Oh, okay, I hadn't thought of that. I mean, full disclosure, I had prepared these slides or most of these slides previously, and the default is that these things are confidential. But in this particular case, if it were confidential, then I wouldn't be, sharing it with everybody. So these slides are not confidential, and in fact, a PDF of this slide deck, I think, should also be available to you afterwards, if I'm not mistaken. So yeah, thank you for asking that. That's impressive. But yeah, so in this particular case, it's actually not confidential. I mean, the stuff that's here is not confidential.
Thank you. All right, this next question is, from the kind of questions, I wonder if not all of us understand the basic relationship of the measurement devices to the beam path. Could you explain that a little bit?
Measurement devices to the beam path. I'm not sure that I understand the question. Could you please maybe elaborate the question just a little bit?
Let's give him a moment to see if he'll
Sure.
elaborate. And if not, we can always get back by email after as well.
Right, if you mean the sensitivity of the dependence of the reading of the sensor to the incidence angle, that might be one thing. I'm not sure that that's what you mean, though.
He said yes.
Oh, that is what you mean. Okay. So yeah. So all right. That's actually a good question. I was about to say that in sensor specifications, it's probably there, but the truth is no, I don't think it is. We have on our website in Ophir, we talk about that in one of the FAQs, but okay, we all know that that's not in anybody's face when they're looking for a particular sensor. So it depends on the absorber type. For the kind of absorbers that we're talking about here, the angle dependence is not zero, but it's generally pretty small. It's probably negligible out to incident angle of probably even up to a few tens of degrees from normal. Even in the case of volume absorbers where the light is passing through a thickness of material, and if we're coming at an angle, it's passing through more of a thickness of material because of the angle. But the truth is, even then we don't care because it's getting absorbed, that heat is being measured, and then we're fine. So like in the case of Ophir, and I imagine other manufacturers also, there are curves or other data of the measured, the numbers, the effect of the dependence of the reading on incidence angle. In general, I don't remember specifically, let's say for the CM, but for pretty much all the absorber types that I had in that little chart that I showed near the end, the angle effect is pretty small, certainly within a few tens of degrees of normal. And secondly, if you've got, let's say, diverging beam, then even less of a concern because a diverging beam is a cone that has all angles in it and only a small percentage of the light is at the outermost angle. So you would have to do a weighted average. So I remember once, actually, I remember being asked this question some years back for our standard, the more traditional surface absorber, regular run-of-the-mill thermal sensor, and they're up to like 40, 50, 60 degrees incidence angle, the effect was negligible. So I would imagine for most of these kinds of absorbers, the effects are small. Very large angle of incidence, it might not be so small. Specific details, obviously, each manufacturer will give you the numbers for whatever specific sensor type you're asking. But I think that's a pretty good generalization.
All right, thank you. And I think that's all the questions we have for now. Everyone, if we have not already answered your question, please look out for a reply from us later. If you think of another question or would like to request a copy of today's slides, you can let us know by emailing webinar@photonics.com. That's WEBINAR@photonics.com. And just a final note, this whole session was recorded. It will be available on the Photonics Media website shortly, and you will receive a link to that in your email. I'd like to thank Mark Slutzki from Ophir one last time, and thank all of you for participating today. This webinar was sponsored by Ophir, LaserPoint SRL, and DataRay Inc., and it was hosted by us at Photonics Media. Thank you.
Thank you, everyone. Thank you.